Hello and welcome back to Stat 201. This week we're going to talk about Chapter 5, which is the topic of probability. If you think back to where this falls into the big picture, if we know what the characteristics of the parameters are, or rather if we know what the characteristics of the population are, the parameter values, then we can make statements about how likely the observations are that we observe. And so that's what we're going to learn all about this week. And we're going to, in order to do that, need to set up a framework, a proper framework for doing that, and then talk about how to assign numbers and so forth. So let's go ahead and jump into what we've got going for this week. Probability is all about following: random experiments probability, rules of probability, independent events, contingency tables, tree diagrams, Bayes theorem, and counting rules. So we'll try and make a video for each of these, or I might combine a couple depending on how long they go. Here are the learning objectives. I'll let you push pause and look at those if you like, and the rest of the learning objectives. So we start off our discussion of probability by talking about random experiments. And a random experiment is a process that can be observed, and the outcome of the process is not known in advance. So that's what we call a random experiment. The randomness has to do with the part that we don't know in advance, and the experiment is just a trial, or think of it as a process that we can repeat over and over again. The sample space then for the experiment is the set of all possible outcomes from that experiment. And we denote the sample space as capital S. A sample space with a countable number of outcomes is discrete. We'll talk more about that a little bit later. We can actually write down the sample space when we have a discrete random variable. And if we're going to roll a six-sided die one time, then we can write down the sample space S as just being the values 1 through 6 as shown here. And when we have two dice that are rolled, or a pair of dice, we have a sample space that's a little bit more complex. Instead of there being only 6 elements, there are now 36 elements, 6 for each of the two die, and combine those together to get all of the possible outcomes when we roll a pair of dice. If we're talking about what's called a continuous variable or a continuous measurement, the sample space can't be listed out, but can be described by some sort of rule. So for example, if we're going to talk about the length of a phone call, the sample space looks like this. It says all x such that x is positive. So if you have a phone call, you know that it's not length 0, and who knows when it's going to end. Could go on for the rest of forever, possibly. Another example would be if we're going to talk about the GPA of a student, we could say the sample space is everything between 0 and 4.0. And even though the grade assignments are given discrete values, the weights for each of those, the grades, if you took enough classes, in theory you could possibly hit every single number between 0 and 4. Although that is kind of a stretch, so I'm not sure this is a very good example, other than to say if you could score anything between 0 and a 4, then that is continuous, because there's an infinite number of values between 0 and 4, and you can't count them, because if you try to say what's the second, the smallest one obviously is 0, what's the next one? And if you were to propose some number, say 0.001, I would say, well, divide that number in 2. Is that in the set? And you would say, yes, it's still in the set. So divide that number by 2, and that's still in the set. So you can't ever come up with the second smallest value in the sample space if we're talking about a continuous measurement. And that's what makes it continuous. An event is any subset of outcomes in the sample space. That could be a single outcome, in which case we would say it's a simple event or an elementary event. And the sample space consists of all of the simple events or elementary events, and we're going to denote those as E sub I. So we can say E is just equal to all of the simple events. Sorry, S, sample space, is equal to the combination of all of the simple. An example of this would be if you're going to look on Amazon's website for books and music. There are 7 categories, or at least there were at the time of this printing, and those categories are countable, so they're discrete, and here we can write them all down: books, DVD, VHS, magazines, newspapers, music, and textbooks. We could make complex events or composite events by combining these things together. For example, we might say electronic media might be all music, DVDs, and VHS, although VHS, who knows what that is anymore. We might have print periodicals, that's all newspapers and magazines. And this can be shown by using a very useful tool called a Venn diagram. And a Venn diagram is just a representation of the universe as we know it. And we would say everything that happens inside of this this rectangle. So the rectangle represents the sample space, and we have then music, DVDs, and VHS all inside of event A, and newspapers and magazines all inside of event B. That leaves us with books and textbooks that are not inside of those, and this is a very good representation of what events look like. The probability of an event can then be assigned as a number that measures the relative likelihood that the event will occur. In this case, when we say relative, we mean relative to the entire sample space, and that can be represented by just the area associated with the event inside of the Venn diagram. So if we could somehow find out what this area is, we would know what the probability of the event A is equal to. And we will denote that as P of A, and there are a few properties and rules that probabilities have to follow in order for all of this to make sense and be consistent. And the first one is that the probability must be in the interval between 0 and 1. So in other words, no probabilities can be bigger than 1, no probabilities can be less than 0. So we would say probability of A is between 0 and 1, and that's inclusive. So it could be between equal to 0 or equal to 1. If it's equal to 0, it has a special name. It's called the empty set. If it's equal to 1, it has a special name. It's called the certain event. And if probability of A is equal to 0, that means the event cannot occur. Actually, it doesn't necessarily have to be empty, but it can occur. Can't occur, I should say. And if probability is 1, that means the event is certain to occur. The next rule that has to take place with discrete random variables, at least, is that the sum of the probability of each of the elementary or simple events has to equal 1. So the probability of the sample space has to equal 1, and that's made up of all of the elementary elements. So for example, if you went on a shopping spree and we had the following percentages, we could compute the probability of, or rather we could see that the probability of somebody using each one of these methods to pay on a shopping spree sums up to 1. So 32% use credit cards, 15% use debit cards, cash is 35%, and 18% use a check. So notice that these are actually not probabilities, these are percentages, and there's a difference between a percentage and a probability. And the difference is that probabilities are between 0 and 1, and percentages are between 0 and 100. So if you divide the percentage by 100, you'll get the probability. Credit card 0.32, debit card 0.15, cash 0.35, check 0.18. So these things really tell us the same information, but you'll find in some of the homework questions that they will ask for the probability of something taking place, or the percentage, the proportion in percentage, and you'll need to make sure that you answer that correctly. using either the decimal or the non-decimal. There's actually three different approaches to probability. The first one is what we call the empirical approach, or the relative frequency approach, and that allows us to assign the probability or define the probability of an event based on taking a sample and repeating that sample over and over and over again. And one way to think of this is to have an experimental sample space. In other words, you would perform the same experiment over and over and over again and record all of the different outcomes that you had every time you did that, and then you could go back and look at that experimental sample space, which would be different than the actual sample space in that it would be much larger, but you could count the number of times each of the events occur, and we would call that the frequency, denoted f of I. So, for example, if we wanted to estimate the rate of student loan default, we would say, what's the probability that a student defaults? We can define that to be f over n, where f is the number of defaults and n is the number of loans. Okay, so this is a very useful method for assigning a probability, and it's all kind of based on this thing called the law of large numbers, which says as the number of trials increases, then the empirical probabilities approach the theoretical limit. And so, for example, if we wanted to flip a coin 50 times, we would expect the proportions of heads to be near 50%, but we wouldn't expect it to be exactly 50% necessarily because of randomness, and we'll talk more about what randomness is later in the course. If we have a small sample, then the ratio that we see could be anything. If we only had 3 flips of the coin, it wouldn't be that unlikely to see 1 heads. If we had 13, maybe 7, and so forth. So if we had 50 flips of the coin, we would expect to see 25, but 28 would probably be okay too. Certainly it would be something that we shouldn't be surprised to see. But the point of this is that as n gets large, then the value, the proportion, is going to go closer and closer to 50%, or 0.5. And in fact, that's what happens. Here's some computer simulations that are done where we have, first of all, 10 flips of the coin, and you can see that the first 3 are all heads, and then we get a tails and a tails and a heads and a tails. Every time this goes up, we have a heads. Every time it goes down, we have a tails. And you can see what happens when we start taking more and more of these things. 20, we start coming down closer to this 50%, this theoretical 50% line. If we keep going, it's entirely possible that we get deviations up here like this. But the point is, eventually it's going to come down. When we take 100 flips of the coin, it's going to start coming down here. So that's one way to describe probabilities and calculate probabilities. There are 2 others. The next one is what we call the classical approach. And the classical approach, often sometimes called the a priori approach, says let's treat every single experiment, or rather outcome, event, as equally likely, and then we're going to just count the number of ways that the event that we're interested can happen and divide that by the total number of possible outcomes for the experiment. So this is based on logic, not experience, and in some ways this is better than the frequentist approach, because what are the obvious problems with the frequentist approach? We'll talk about that in just a minute. So you can imagine if we're going to flip a coin or roll a pair of dice, we don't actually have to do that. We don't have to perform the experiment, because if we're going to flip a coin, we know that there are 2 possible outcomes, heads and a tails. And so with the classical approach, we would say they're equally likely. So what's the probability of heads? It's just 1 divided by 2. which is 50%. So there's two possible outcomes. One of them is the one we're interested in. If we're going to roll a six-sided die, we could say, what's the probability of rolling a 7? Using the frequentist approach, we could just roll the die, the pair of dice, a whole bunch of times and count the number of 7s that we get. But if the dice are fair and unbiased, then we could just count the number of ways to get a 7 and divide that by the total number of outcomes. So we write out the sample space like we did previously and say these are all the times when we get a 7, and there's 6 of those things, and there's a total of 36 possible outcomes. So that brings us into the subjective approach. This is the last approach to probability we're going to talk about. And the subjective approach says, well, what do you think the probability is? Or what do you think? What's your judgment or your guess or your gut feeling, or some way that you want to, any way that you want to come up with a probability is fine if you're going to use a subjective approach, probability. The problem with willy-nilly coming up with the probability of an event taking place is that generally you should be worried about your credibility and about your expert opinion, and you have the opportunity a lot of times to be able to put your money where your mouth is, so to speak. In other words, if you think the probability of some event taking place is very high and somebody else thinks that probability is very low, then they might enter into a bet with you that the event won't take place. And if you really think it's high and they really think it's low, you guys should be able to agree upon a payout that would be mutually beneficial to both of you. In other words, how much do you get if you win? How much do you lose if you lose? And come up with some number that really forces you to be honest about the probability that you think really should be attributed to the event. This is something that's used when there's no repeatable random experiment, or when there is, as in the case of the frequentist approach, but also when the classical approach doesn't work as well, we're oftentimes left to the subjective approach. And if life as it does gets very complicated, it's oftentimes very difficult to do what it is that we want to do, and that is to find the probability. In other words, say a basketball game, you want to know the probability that a team's going to win. You could use the frequentist approach. You say these two teams are playing, how many times have they played before, how many times has each team won, and you could use that to come up with a probability of each team winning. That is the frequentist approach. The obvious problems with that are that every time they play, they're in a different location, maybe they have a different team, maybe someone's hurt, maybe the coach is sick, maybe one team is in the middle of finals week and the other team's not. And there's all sorts of things that prevent each of those meetings from being identical to each other. And so the experiments are not identical. So use the relative frequency approach is not the best idea in that situation. The classical approach says, well, the probability that one team's going to win is 50% and the other team's going to win is 50%. It's because there's two teams, only one possible outcome, excluding the possibility of a tie anyway. And so at that point, you're left to the subjective approach, which says, let's use our judgment and take into account what we know about each of the teams, the players, the location, the so on and so forth, records against other teams, and let's convert that into some number between 0 and 1, representing the likelihood that one of the teams is going to win. And this turns out to be something that we all do all the time. If we're going to cross the street, we're only going to do that if we think there's a high probability of getting across safely. So we look both ways. We take into account all the information that we have. based on past experience, we then say, okay, it looks like it's good, you got the clear signal to go, you're going to cross the street. Now that doesn't guarantee that you're going to get across safely. There could be a tornado, there could be a flood, there could be a bank robbery taking place around the corner, and a car speeding away from the bank comes around the corner as you're walking across the street and runs you over. But that's I guess another topic for another time. Typically we have questions that are difficult, and most of the questions in life are difficult, and it's hard to simplify them enough to be able to do this stuff. So that is our introduction to probability. Anyway, we covered the sample space, events, experiments, and the three approaches to probability, and we will use all of them as we go through the rest of this course. So check out the next video. We'll see you there.